Our next example of finding critical points then is this equation, x cubed minus 3x. Again, we're choosing some simple polynomials to differentiate now just so that we can practice with the process, and we'll amp it up to some rational functions in our next lesson. But in this one, we're going to find the critical points. Of course, we know they're going to happen when the derivative is equal to 0, so we need to find the derivative. And the derivative, of course, of x cubed is 3x squared, and the derivative of negative 3x is just negative 3. Set that equal to 0, and that'll be where we'll be able to find our critical points. Solve for x, so of course bring the 3 over, divide both sides by 3, and we get x squared equals 1. Remember, when you take the square root of 1, we're going to have two possible answers, a positive or a negative 1. That's because there are two critical points. So each of them will generate their own critical point. By subbing in back to the original equation then, we're going to plug in f of 1, plug that in, 1 cubed minus 3 times 1 gets us negative 2. And if we plug in negative 1, we plug that back into the original, we'll get another critical point at x equals negative 1 and y equals 2. So right now, when we go off and graph these, we will only be able to see these 2 points. We might have a guess of what this graph looks like, but we want to verify that these are indeed maximums or minimums. So we're going to start again by doing our table. So we set up our table again with the intervals on the top and the derivative and what the function is doing. And we want to investigate now in two spots. We want to investigate when x equals negative 1 and x equals 1. For those we know the derivative is 0. We know that it's going to be flat. The tangent's going to be flat at both these spots. But the question is, what does it do before and what does it do after? So if we're talking about before this first critical point, we're talking about everything less than negative 1. Everything less than negative 1. And if we're talking about after this critical point, we're talking about everything greater than 1. And then that leaves this interval in here. What's the graph doing in between these? So between negative 1 and 1. You notice that I don't have equal signs on these inequalities because the equals belong here. It's not when x is greater than or equal to, it's just when x is greater than 1. I know what it's doing it when x is equal to 1. So we need to investigate the derivatives, or the tangents, in these intervals. So again, we're going to look at the derivative and recognize that it's easier to be able to figure out a factored form of that. So if we take out a 3 as a factor, we're left with x squared minus 1. That can factor even further to x squared plus 1 and x squared minus 1. That way, when we sub in test points within these intervals, you can get figure out what the derivative's doing. So let's test it when x is less than negative 1. So any point less than negative 1, I'm just going to imagine negative 2 in my head. Of course, the 3 is always going to be positive. If I put in negative 2 plus 1, that's going to stay negative, and negative 2 minus 2 is going to go negative. So I'm going to have a positive 3 times a negative outcome here and a negative outcome here, which is going to end up being positive. So that means that the graph before must be increasing. The interval in between is any spot in between here. So any number between those, an easy one is 0. So again, it'll be 3. If you put in a 0, that'll be positive, and that'll be negative. So a positive times a negative ends up being negative. So that means the graph is decreasing in this middle interval, which is probably what we expected it to do. And then you choose a number for x greater than 1, something like 2. That'd be positive, positive, and positive will get me a positive, means it's increasing after. So then if the tangents are positive, that means the graph's increasing before and decreasing after this critical point. That means that this one must be a local maximum. And if it's decreasing then increasing, then this is a minimum. And remember, these charts are all the proof of what we suspected the graph to look like. And here is then the beginning parts of that graph. Now if we wanted to find more information about this, we could do x-intercepts, y-intercepts. I don't know if it goes through 0 or not. I think it does. But this is just that part of our full process. We're going to do a final example really quickly, just a simple one, x cubed, to introduce something else that might happen. So if we're going to do this one, we'll differentiate it. 3x squared, set it equal to 0, divide both sides by 3. And of course, the square root of 0 is just 0. So we have one critical point appearing at 0. We plug 0 in here, and we get that. So we know that there's a critical point at 0, 0. So if we're going to graph this, we know that there's a point right there at 0, 0. The question is, what's it doing? Is it a max or a min? Now, again, you might already know the answer to this, but what's going on? Because it's neither a max or a min, right? I think the x cubed graph looks something like this. So what's going to happen in this situation? Now, again, that's because I know what x cubed looks like, but if I have a function I'm not sure of, all I have is a point. I don't know if it's a max or min or what. So let's find out. So we'll set up our intervals again, and this time our interval of x equals 0. We know it's a flat line here, the tangent's flat. We want to know about before and after. So again, we're looking at the derivative. So we're looking at 3x squared. Again, you could factor that into an x times x if you wanted, but you know that x squared is always going to be positive. So the positive 3, and regardless if you put in a negative 1, you're going to go negative 1 times negative 1, or negative 1 squared is going to be positive. So you know that it's increasing to 4. And if you put in an x greater than 1, something like 1, or x greater than 0, sorry, put in something like 1 or 2, it's all going to be positive, and it's increasing after. So this graph is increasing before and after. So it's not a local max or a local min. But the math still suggests that it's flat at that point. And we know something about x cubed, that it does. It comes along and it flattens out there for a moment, and then it continues on. So it's not a local max or a min. It doesn't, it's not going from increasing to decreasing. It's going increasing and increasing. So this point is no longer called a max or a min. So what is it called? Well, it's actually called a point of inflection. So it's still a very critical point. It's still a spot where the derivative is equal to 0, but it does look a little bit different because um, it's not a max or a min. So it does have its own name, it's the point of inflection. It will appear as a critical point, but in your chart you'll discover that it's only a point of inflection, and the graph does that. So those two examples hopefully were helpful. There are a bunch of practice questions if you wanted to just work on this, but the sketching and the stuff we're going to be doing in the next lesson, we'll be putting it all together, and that will be another opportunity for you to practice this skill of finding critical points.